Good morning, dear students. In the last videos, we have finished up to the physical equilibrium processes, which we have discussed about the phase transformation, solid to liquid, liquid to vapor, as well as gas to liquid to gas, that is liquid to vapor, solid to liquid, and different type of physical equilibrium in a phase transformation as well as dissolution. And uh, even the summarized note also I have given. Now today we will start with the new topic, that is equilibrium in chemical processes. So if we are discussing about equilibrium in chemical processes, definitely we will have to think about a chemical reaction. So here let us think that this is one hypothetical chemical reaction which is shown, and we know that chemical reaction is always having reactant and product. So this is just an idea that A plus B are the reactants. When they react, they produce the products C plus D. And the double arrow which shows here, the forward and the backward reaction. This means that equilibrium establishment is possible. That means when reactant reacts, they are giving products, and if the products again start reacting, they are giving back the reactants. And if this happens in both the type of reaction, forward and backward, then definitely equilibrium takes place. Now when equilibrium takes place, when the rate of reaction of reactant, that is forward reaction, and rate of reaction of product to reactant, that is backward reaction, becomes equal, we can say equilibrium is established. So here reactant reacts to form products, and as soon as the reactant starts to react, what happens? In the initial stage, the reactants will be at the highest concentration, because at the initial stage they just start to react. At the same time, product is having zero concentration. So the concentration of reactant in the initial stage is small and concentration of product is zero. Now gradually the reaction starts. A and B reaction starts, that means they will start reacting with each other. As soon as they start reacting with each other, what happens? The reactants start getting consumed, right? Utilization of A and B will take place to give the product C and D. So the concentration of A and B gets decreasing, and slowly and gradually the product starts forming. So concentration of product will start increasing. When concentration of reactant decreases and concentration of product increases, then it is the forward reaction, right? So what we can say that gradually the reaction starts and concentration of products, that is C and D, continuously starts increasing, and reactants, that is A and B, continuously they starts decreasing. So the rate of forward reaction decreases and backward reaction increases. This reaction decreases and here it will be increasing. Now the reaction starts backward. That means it takes place that maximum amount of reactant gets reacted and product is now almost formed. When this product now becomes reactant, and they will start giving back reactants. So at that time C and D will be reactants and AB will start getting as a product. So that will be the backward reaction. So reaction starts backward. So concentration of product, that is CD, will decrease because they will be now reactant, and concentration of reactants, that is AB, will increase because they will be product then. So rate of backward reaction now decreases and forward reaction increases. Thus what happens? Reactant to product and product to reactant. These are the opposite reactions. So both opposite reaction takes place, and when both rate that means rate of reactant to product forward and rate of product to reactant that is backward. When both the rate is attaining a equilibrium, that means similarity, then we can say that equilibrium is established. That means the reactant no longer can form the product then, and product no longer can give back the reactant. At certain stage, at specific condition and at certain stage, the reactant will stop reacting to give product, and product in the backward reaction will also stop giving the reactant back, and that particular stage is attained, that is called equilibrium. And this equilibrium, when we say, we can say that it has attained a dynamic equilibrium. That means dynamic nature. Dynamic nature, it means, once again in physical process also this is discussed. Dynamic, that means we feel that actually it is now static, nothing reaction is taking place, but still the somewhat activities is still going on, which is not showing here as a concentration. But some of the reactions in chemical processes are there which even gives the evidence that yes, it is dynamic in nature, right? Now let us see here the graph of equilibrium, concentration versus time. The y-axis here shows the concentration and x-axis here shows the time. Here the red line shows the reactants and blue line shows the products. So at the initial stage at time 0, that means at the very starting stage, the concentration of the reactant, you can see it is very high. And with the time, as the reaction starts, with the increase in the time and reactants will start reacting, see the arrow which is gradually going downwards, that is decreasing. At the same time, initially the product was at the 0, right? No concentration is shown here. And gradually as the reactant starts getting consumed, the products start getting increasing. And a particular specific stage, it attains that this reactant, it starts getting parallel to the time axis, and the same there is blue line, that is the product axis line, also becomes parallel to the time axis. This is see the parallel, right, to this time axis. At this point, now onwards, both are parallel to the time axis. That means there is no change on concentration now. And then this particular point is termed as the equilibrium establishment or equilibrium attainment point, right? So here red line shows reactants which initially at 0 time is having more concentration, and blue line is showing product which is 0 concentration at 0 time. When reaction starts and with the increase in time concentration of A plus B decreases and C plus D product increases. At certain stage, this is the certain specific stage, that both curve becomes parallel to the time axis, which shows no change in the concentration there onwards, and this stage is termed as equilibrium. For reversible process, when I say reversible process, it means forward and backward both processes are possible. Then such type of processes are called reversible processes, and for reversible processes, equilibrium can be established from either side. From either side, it means from forward to back, that is from reactant to product forward, and from product to reactant, that is backward. The state of equilibrium which is attained is dynamic in nature. It means now it appears to us that now here onwards no any further any separation of atoms takes place. That is, we find it that it is static, but actually some gradual changes still keeps on. That is called dynamic nature of the equilibrium, and this is evidently seen in chemical equilibrium, which is shown to us by scientist Haber. Scientist Haber has carried out many different experiments to show that equilibrium is dynamic in nature. It means we say that equilibrium is attained, but that is now no more concentration change is taking place, but still there are some activities, some separation of atoms to unite with or to combine with other atoms, and new formation in a gradual form is still taking place in some of the formation of the compound. And so it is said that chemical equilibrium shows the evidence of the dynamic nature. Scientist Haber, we know that Haber's process. In 10th standard we have learned Haber's process, formation of ammonia by the usage of hydrogen gas and nitrogen gas. Even in the chapter of hydrogen we will come across this, and in organic compound also, but here we will still understand, or we will discuss about it to understand the dynamic nature of equilibrium. So scientist Haber has used nitrogen and hydrogen for the production of ammonia. Haber's process is giving evidence of dynamic nature. Here is an example of it. N2 plus 3H2 with the help of the catalyst iron at 400 degrees Celsius and 200 atmospheric pressure. When these two reactants are reacted, they give ammonia, that is NH3. 1 mole, that is 1 mole concentration of nitrogen, 3 mole concentration of hydrogen when react together gives 2 mole concentration of ammonia. And he has also done this experiment with the D2. Now what is D2? D2 is the deuterium isotope of hydrogen. Hydrogen is also called protium, having 1 proton and 1 electron, whereas deuterium is having 1 electron, 1 proton but 2 neutrons. So there is a difference in the mass. No other chemical properties is different for hydrogen and deuterium. Only the difference between them is the difference of mass. So here also he wanted to see that really this is the similar, that is hydrogen and deuterium. If they show the chemical similarity, then they must show the similar reaction. So again N2 was reacted with D2, and again the ammonia in the form of D3 is produced, and D3. So from this he got that because of the isotopes there won't be a difference in the reaction. But now what he wanted to see, that really the equilibrium is dynamic. You can see this is equilibrium. Double arrow is shown. Equilibrium here, it means when these two reacted, ammonia is produced. Now when this ammonia is decomposed, again nitrogen gas and hydrogen gas will be produced. Same thing with the deuterium also. That is, ammonia in the deuterium form will give nitrogen gas and deuterium gas, right? That is the isotope of hydrogen. So thus both this reaction equation shows that they attain equilibrium. But now when this both reaction species are all together mixed, all together, that means this 3 and this 3 all together, when they are mixed, then at the same condition, after a while, all these 6 species, though they were at equilibrium, they will be observed with some different species. That means some other combinations of the atoms has also existed, and they existed as N2, H2, NH3, D2, ND3. They were all there. But now along with them the allotropic form were observed that were N2H2HD. HD, that means one atom of hydrogen and one of deuterium. Then NH2D, that is 2 hydrogen 1 deuterium, and here NHD2, 2 deuterium and 1 hydrogen. So this was the evidence that though these all N2, H2, NH3, ND3, D2 were all have attained equilibrium, then again this allotropic formation has still found after a while. It means slowly and gradually the separation of atoms took place and they combined among themselves only in a different allotropic form. So this is the dynamic nature, that equilibrium is attained and then also the formation of new species has arise. So this was the evidence that although the equilibrium was attained, yet the separation of species were found. This was because the reaction was still going on and atoms were still separating and were forming combinations of atoms with other atoms. This means that both the processes are still going on, and this proves the dynamic nature of equilibrium. Equilibrium can also be achieved from NH3, that is the backward. NH3 when decomposed it will give N2 and H2 gas again back. Right? So here the graphical representation of Haber's process. This is the concentration axis. This is the time axis. This is 0 initial position. Nitrogen is only 1 mole concentration, whereas hydrogen is 3 mole concentration. So here we can see 1 mole at this concentration and hydrogen at higher concentration. When these two start reacting at the initial stage, we can see that the ammonia formation takes place in increasing manner, and at certain stage it becomes parallel to the time axis. That means the equilibrium is attained. And again when this ammonia is decomposed, it will separate back hydrogen and nitrogen. So this is how scientists Haber saw that even after the equilibrium is attained in the isotopic form of the hydrogen, then the new allotropic form as NHD2, NH2D, HD, a new separation of atoms took place, and this is what that equilibrium attained, that is static concentration has attained and still dynamic nature has taken place. One more example is here, equilibrium formed between hydrogen and iodine. Here you see H2 plus I2 gives 2HI. Now here the equilibrium is with the similar number of atoms. Hydrogen 2 in the reactant, in the product also 2. Iodine 2 in the reactant, in the product also 2. So this is again an equilibrium which shows the similar number of atoms in both the forward and reverse reaction. Here in forward and backward reactions, the same number of atoms are attaining equilibrium. That is, they are in the same order as I told. Same concentration in reactant and product side. So, they exist with same mass. And this is observed that if total number of hydrogen and iodine atoms are at same in a given volume, the same equilibrium mixture is obtained from both the sides. And this specially takes place at the specific conditions. Here it is shown that this is the initial stage. At the initial stage, when hydrogen and iodine are reacting, then gradually they decreases down, right? And here they will show little parallelity, not exact, but here it shows little. In the same way, when the increase in the product starts, it also shows a here little parallelity, and then this is termed as equilibrium point. And if the reverse reaction takes place, then if this is time again swing back. So here it starts again increasing and it will start getting decreasing, right? So this is the forward reaction and this is the reverse reaction of the hydrogen iodine giving hydrogen iodide. So these two were the different examples studied, different experiments which is studied by Hebers, that particular substance when react and when their isotopical form react, they give the dynamic nature to the equilibrium, and particular element when they react with the same number of atom and give same number of product, as well as the same product when again give back the reactant, the number of atoms in both the reaction forward and backward remains the same, right? So this is all the discussion about dynamic nature of equilibrium, and now we will study about equilibrium law and equilibrium constant, right, in the next video. By the time, thank you.